The final step in our RCM study is to perform simulations to optimize our maintenance strategy. To demonstrate this, I'll use a completed version of the project we were building in the last tutorial, in which we defined the maintenance tasks for all our assets. Before we run any simulations, we will want to set our simulation options. On the Lifetime tab, we can set the system lifetime. This is the period of time over which we want to evaluate the system. Time profiles allow us to view results over intermediate periods throughout that life. We can also set whether we want to optimize maintenance intervals to minimize cost or to maximize availability. On the Simulation tab, we can set the number of simulations to be performed. The general rule is that more simulations produce greater accuracy, but at the trade-off of more computation time. We can also define safety, operational, and environmental criticality targets. We'll see how these are used later. Now let's take a look at optimizing maintenance for the casing leaks failure mode on the screw feeder of our extrusion unit. I'll perform the optimization on the Strategy tab. Here we see all possible maintenance actions we can perform to mitigate this failure mode, though we'll focus on the planned maintenance task for now. First, I'll click the Evaluate Strategy button to find baseline figures for this cause. I can see the cost, criticalities, downtime, number of failures, unavailability, and outage frequency if we were to adopt a run-to-failure maintenance policy. Next, we will optimize our planned maintenance task. We do this by selecting the planned task and then clicking the Interval Optimization button. We'll first specify the interval range we want RCM cost to use. In this dialog, we'll set the number of different maintenance intervals we want RCM cost to try. We'll set the time of the first maintenance interval, and then we'll set the time increment for each additional interval. This is telling RCM cost we want it to evaluate 30 different maintenance intervals. The first maintenance interval should be 730 hours or 1 month. Each subsequent maintenance interval will be 1 month longer than the previous one evaluated. It's important to set the interval ranges appropriately to make sure we capture the optimal maintenance time. We'll talk about that more later. After specifying the interval ranges, we can run the optimization simulations. When RCM cost has performed its optimizations, it will show up as a plot comparing the cost for each potential maintenance interval. The x-axis of this plot is the maintenance interval, and the y-axis on the left is the cost. The blue line correlates each maintenance interval with its cost. On the left, when we have a very short maintenance interval, where we're doing it every month, we see a high cost from overperforming maintenance. We're spending money on maintenance that doesn't have a return on the investment. On the right, with a longer maintenance interval, we again see a high cost from underperforming maintenance. We're experiencing failure downtime that could be better mitigated with a more proactive maintenance strategy. At the low point of the curve, at 4,380 hours, or 6 months, we find our optimal maintenance strategy. This is where the cost of the maintenance and the cost of failure are in balance, as all things should be. The red, green, and purple lines refer to the safety, operational, and environmental criticality. The y-axis for criticality appears on the right. RCM cost optimizes the cost with an eye on this criticality. It's possible that the optimal strategy to minimize cost will come with an unacceptable criticality. This is most often seen when a run-to-failure policy is cost optimal. For this reason, RCM cost also displays the criticality for each potential maintenance interval. The criticality targets that were set in the project options can also be displayed on this graph for comparison. To do this, we can select the Plot Options button, and then check the Show Safety, Show Operational, and then Show Environmental Targets. We'll need to rerun the optimization simulations to update the plot. Once we've done that, The targets will show as dashed lines on the plot. RCM cost will recommend the maintenance interval with the lowest cost that still meets the criticality targets. If you like this recommendation, you can accept this recommendation by clicking the Accept Recommendations button. RCM cost will enable the planned maintenance task and set the interval accordingly. We can then reevaluate the strategy to find the cost, criticalities, downtime, number of failures, unavailability, and outage frequency if we were to adopt this maintenance strategy. Perhaps most importantly are the benefit ratios. The benefit ratio is the cost or criticality with the current strategy divided by the cost or criticality with a run-to-failure policy. For instance, in this example, it costs 23.5% as much to perform planned maintenance every 6 months as it would to not perform it at all. In other words, performing the PM at the designated interval will save us about 76% over the lifetime. The optimization can also be performed from the plot view in the right-hand window when the maintenance optimization plot is selected from the plot type selector. The buttons to specify the interval range, to perform the optimizations, and to accept the recommendation appear in the right window toolbar. We can also globally optimize all maintenance tasks all at once by selecting the Simulation Auto-Optimize Intervals for Tasks menu option. It's important to remember how the interval range can affect the recommendation. For instance, for the drive shaft shears failure mode, RCM cost will recommend a run-to-failure maintenance policy. However, when we look in more detail at the cause, we can see that the characteristic life for this component is around 44,000 hours. However, our interval range only considers up to about 22,000 hours. If there is an optimal point, we are most likely missing it due to the constricted interval range. To get a better optimization result, we will want to make sure our interval range covers the expected wear out of the component. In this case, I'll set the initial interval to 2 years, or 17,520 hours. After rerunning the optimization, I get a new recommendation of planned maintenance at 21,900 hours, or 30 months. After this time frame, the cost once again increases the longer we delay the maintenance. We can simulate the entire system by selecting the Start Simulation toolbar button. When the simulation is complete, the Simulation Results dialog will give us overall results for the system cost broken down into categories. We can also see individual results for each cause, for each effect, and for each resource, that is the spares, labor, and equipment, if applicable. Many of these results can also be viewed as a plot. When the Plot Right Window View Mode option is selected, we can see these results from the Plot Type selector. The Cost Profile plot shows a breakdown of overall costs for the system per profile interval, color-coded by category. The Labor, Equipment, and Spares profile plots show the usage of each resource. The Effect Profile plot shows the number of effect occurrences per interval. Perhaps most useful is the Contribution plot, which shows the contribution from the top 20 causes to system cost, again color-coded by category. This is a useful tool for figuring out where we can make improvements in the system. In this project, we see that cause elec1.a.1, that is a power surge leading to fuse blowing, has the highest cost of any system failure mode. If I click on the bar in the bar chart, it will open the Cause Properties dialog for that cause. This way, we can investigate why it might have such a high cost, and what we can do to lower the cost. The fuse blowing will result in a major loss of production. In the Failure tab, we see that the failures are exponentially distributed, meaning preventive maintenance does not really lower the effective age of the component, and thus is not really going to be an effective strategy. No realistic inspection task can be performed to detect the failure mode. On the Strategy tab, we note that the component has a very long failure downtime, despite the fact that the corrective maintenance has a relatively quick task duration of only half an hour. The reason for this long downtime is due to the lead time on the spare parts. A spare fuse is needed to correct the failure. If we investigate that spare fuse, we see that we are not currently storing any spare parts at level 1 or at level 2, meaning any required spares will take 480 hours to arrive from the factory. This may be a good time to use RCM Cost's spares optimization to determine the optimal number of spare parts to keep on hand. We can access the spares optimization feature from the Simulation Optimize Spares menu option. From the bottom of the dialog, we can select a spare to optimize. I'll choose the spare fuse. Spares optimization works like interval optimization in that a range of possibilities are considered and the lowest cost alternative is recommended. For spares optimization, this range is the number to store at both level 1 and level 2. RCM Cost will simulate all possible combinations of level 1 and 2 storage, balancing the cost of spare storage against the cost of the extended outages due to logistic delays on obtaining replacement spares. For the spare fuse, I will tell RCM Cost to consider between 2 and 4 spares stored at both level 1 and at level 2. Once I have set the range for the spares, I will optimize the spares by selecting the appropriate button. As noted, RCM Cost considers all combinations of level 1 and 2 storage levels, and produces a graph showing both cost and unavailability for each combination. The x-axis is the spare level, where the number shows the level 1 capacity first and level 2 second. The left y-axis is the cost, and each spare level is broken down into blue showing the storage cost, and pink showing the unavailability cost. The right y-axis is the unavailability, where the red line shows the unavailability for each spare level. For the fuse, RCM Cost recommends storing 3 spare fuses at level 1 and 3 spare fuses at level 2. If we like the recommendation, we can accept the recommendation for the selected spare. As with interval optimization, spares optimization can be performed from the right window as well. I'll first select the spares optimization plot, and then you'll choose the spare that you want to optimize. Once the fuse storage has been optimized, we can rerun the simulations to find the new cost contributions. We see that after spares optimization, elec 1.a.1 has moved from the highest contributor to the 16th highest position. The new biggest contributor is the temperature sensor failure, tmp.1.a.1. Again, clicking on the bar opens the cause properties so we can investigate. In this case, the effect of temperature sensor failure is a major loss of production, a major plant fire, and a small chance of a major explosion. Clearly, this is not a very good design. In this case, simple maintenance or spare stocking levels may not be sufficient. Instead, we might want to redesign the system to add redundancy so we don't have a fire every single time this failure mode occurs. Rather than relying on a single temperature sensor, we might design the system to have 3 sensors, of which 2 must be operating. In the Effect Properties dialog, I can specify 2 additional sensors, and of those 3 total, 2 are required to be operating. If I estimate each sensor to have a fractional downtime of 1%, or 0.01, then RCM Cost's redundancy factor wizard will calculate a redundancy factor of 0.0199. I can apply that same factor to the major loss of production effect as well. Of course, this doesn't come for free. Adding the additional sensors will include a capital cost. I can specify the redesign cost on the Redesign tab. Let's suppose the redesign is estimated to cost $100,000. Once completed, I can rerun the simulations to view the new total cost and contribution. Once again, cause tmp.1.a.1 has moved from the highest contribution to the 9th highest. If I want to view the improvement that I've made from all these changes, I can compare this project iteration to another one using the project comparison option. This uses the library facility, which we've seen in previous training videos. I can use the File Attach Library option to attach any project file as a library. In addition to reusing data from these projects, as we've seen in previous videos, I can also compare project results between the current project and the library projects by using the project comparison plot. In this example, my baseline project is shown at the top, and this new iteration, in which I've done several optimizations, appears at the bottom. This gives me a graphical view to see what sort of cost improvement I've made through these optimizations.